So far we've covered substitutions for indefinite integrals, but we haven't talked about them for definite integrals. So when dealing with definite integrals, or integrals that have bounds that look like this, the process is actually very similar. The first case is to ignore the fact that you're dealing with a definite integral at all. Just deal with it like it's an indefinite integral, and then use that fundamental theorem of calculus at the end to evaluate the bounds based on x. But the second way to do that is to say, all right, well, I'm using a substitution, so I can actually change what the bounds are into my new variable, and that avoids actually having to transform back to x. We can stay in that u space. And we're going to show that example, or we're going to show both methods, first method and second method, to show that those are all both possible ways to do this. So let's get started. In the first case, it looks like my u is going to be this thing, because that's just so much more, that's the more complicated term. So I'm going to say that u is 2x to the fourth plus 1, which gives me that du is 8x cubed dx. So then I can rewrite dx as du over 8x cubed. So then what I'm going to do is, so if you do this just from a notation standpoint, it's really important that you keep track of what bounds you're dealing with. So you should write x equals 0, x equals 1 for what we're about to do, of x cubed times u to the u squared times du over 8x cubed. So notice that those x cubes will cancel. So I can pull the 1/8 out, and I'm saying x equals 0, x equals 1 of u squared du, which then I can say 1/8, 1/3 u cubed from, again, x equals 0 to x equals 1. And then I can pull that 1/3 out, so to get 1/24 u cubed from x equals 0 to x equals 1. Change back using my transformation, 2x to the fourth plus 1 from 0 to 1. Notice that now I don't have to say x, because this tells me, if I don't have an extra notation, it tells me that these variables are in agreement. So when x is 1, this thing is 3. When x is... what did I do wrong here? When x is 0, that thing will be 1, so it should be 2/24. That's... Let me check my notes real quick. Something seems off here. Cubed, right? You can't forget some stuff like that. It's crazy. So when x is 1, you get 3 cubed minus 1 cubed. So that's 27 minus 1, which is 26. 26 over 24. (13/12). My apologies, sorry, that was that's why you gotta have notes, man. You can't just go off the cuff. So for the next problem, instead of transforming back to x, we're gonna stay in u space. So in this one, what we're gonna do is we're gonna say u is 9x plus 9. So that tells me du is 9 dx. It also tells me that dx is 1/9 du. So what we have to be more careful because we have these bounds. So when x is 3, when x is 3, u is 9 times 3 plus 9. So that tells me that it's 36. When x is 8, u is going to be 81. So why am I doing that? Well, the reason I'm doing that is because now, when I take this integral, I get new bounds. So whereas it was 3 and 8 here, it's now 36 and 81. So I have 1 over the square root of u times 1/9 du. So that I can pull out the 1/9 and I can rewrite this as u to the negative 1/2 du. And then when I integrate, I get 1/9 u to the 1/2 over 1/2 from 36 to 81. So I can rewrite that as 2/9 square root of u from 36 to 81. Then I can write that as 2/9 square root of 81 minus the square root of 36. 2/9, 9 minus 6, which is 6/9, which is 2/3. So in this case, notice that I didn't have to go back to x's and juggle these x equals and things like that. I can just carry through the new bounds, and I don't ever have to, I can forget that I was ever in x space at all. I can just stay in that u space. From personal preference, I prefer doing it this way. There are a lot of people that prefer it this way because this emphasizes the same technique for both definite and indefinite integrals, whereas this technique is special only for definite integrals, so I totally understand that. But just from a personal preference, I like doing it this way. But whatever works for you, feel free to use A or B.